Manufacturers of satellite subsystems want to be able to control under software what function their platform performs. So, for example, you may have a supplier who wants to sell a particular piece of equipment into a low Earth orbit satellite program and a totally different geosynchronous satellite program. So, environmentally, the platform that they create has to cope with the worst of all possible orbital scenarios. So they have to cope with the thermal challenges of low Earth orbit, where you're temperature cycling once every 90 minutes. They have to cope with the high radiation environment of geosynchronous. And that poses some significant challenges.
Welcome to Avnet Silica's We Talk IoT. We'll chat with innovators, experts, and business owners to learn how they are implementing IoT and using data to create new business opportunities. I am your host, Stephanie Ruth Haydock. As we push the boundaries of what's possible in space, two pivotal challenges stand out: the hardware components that can withstand the extremities of space, and the sophisticated processing power required to execute space missions. Today, we will explore the transformation in satellite technology, the vital role of commercial off-the-shelf components, and the evolution in processing needs for ambitious space applications. Joining us from AMD is Ken O'Neill, Space System Architect, and representing Avnet Silica, we have Paul Leys, Market Segment Manager for Aerospace and Defence. I'm super happy to have you both on the show, and together we will journey to understand the new space movement's intricacies, challenges, and its future. Welcome, Ken and Paul. I'm really happy to have you on the show.
Thank you.
Thank you. Great to be here.
To kick us off, would you like the chance to introduce yourself, Ken, and what you do at AMD?
Yeah, sure. Thanks. So I'm Ken O'Neill, Space Systems Architect at AMD, and I'm responsible for the radiation-tolerant and space-qualified FPGA line at AMD. And I've been working in the field of radiation-tolerant and space-qualified FPGAs for about 20 years at this point.
Wow. Paul?
So thanks, Ruth, for inviting me. Yes, so I'm at Avnet Silica looking after our aerospace and defence business around the Europe, Middle East and Africa. And I have a very strong passion for the space business, which I've been involved with for maybe 30 years. And I've known Ken also for quite a long time within that 30 years. So I've seen quite a lot of changes in that time. And I must say that it's always exciting, but I have to say it's probably never been as exciting as it is just now. So it's great to come and share our views on the market and listen to answer your questions on the new space and everything to do with it.
And why is it such an exciting time?
We've always had a very active space business in Europe, and we've got the European Space Agency, which is a huge organization supporting the businesses and companies, and with some really phenomenal projects, to do with climate change and exploration to faraway planets. But now we see quite a change. We see a lot of new companies entering the field, young companies, people with ideas, people able to get stuff designed and produced and built in a very much shorter space of time. And in parallel, we also see a reaction from the suppliers to meet the demands of these new space systems with slightly different requirements than we've had in the past. And basically, it's a very, very active time. So we've got the traditional space market still very buoyant. And then we've got this whole new space business that is, very, very exciting. So a lot of really cool ideas coming out of that and a lot of interesting discussions. Yeah, equally, as I said, we've got suppliers like AMD with some really cool products that meet those market needs. So that's why it's exciting.
Interesting. Ken, what role does AMD play in the new space market?
So AMD's role here is as a supplier of FPGAs into the space market. So we have supported the space community for a couple of decades at this point, and we continue to innovate and introduce new products into the space market. supporting new classes of mission. I wanted to kind of go back and touch on what Paul said, when he was answering why the space market is as exciting right now as it is. And what we see is a proliferation of new types of space missions, along with new space companies supporting those space missions. So to give a few examples here, we're seeing new types of commercial space missions with constellations of communication satellites flying in low Earth orbit, providing high bandwidth internet connections, high bandwidth data connections, high bandwidth voice connections as well to parts of the world which historically had never seen that class of service. And in addition to that, we're also seeing commercial imaging, both active and passive imaging, which we've never seen before. We're also seeing new classes of science missions, which are flying sometimes in low Earth orbit, sometimes in more challenging orbits, like at the Lagrange points, in cislunar space, and various other orbital regimes. New planetary missions as well, increasing the amount of attention to Mars, to the moon, and also some Class A missions going out to Jupiter and Saturn. Jupiter Icy Moons Explorer is a European program that launched earlier this year.
Okay.
It's being followed by other programs going to the moons of Jupiter, and then there's also programs going to the moons of Saturn. Very, very exciting times. So back to your question of AMD's role. Yeah, we provide FPGAs for these classes of missions, and we've entered a time where it's not sufficient to supply FPGAs that are just primarily gates, memory, and IOs. We went beyond that quite a number of years ago with the introduction of signal processing resources into FPGAs. Now we have FPGAs that feature two different classes of scalar processor architectures with application class and real-time processors, in addition to DSP resources, in addition to programmable logic resources, in addition to memory, and also in addition to vector processing resources, which is a recent addition to the architecture. So now we have truly heterogeneous computing resources built into FPGAs that are being qualified for space flight and are actually in flight in space today in several different programs that launched earlier this year. So as Paul said, it's never been as exciting as it is right now, and it's always been exciting, but never as much as right now. It's truly wonderful to be in this position, being able to support our existing traditional space customers as well as this new breed of space customers that are coming along.
Brilliant. Just to back up one step, an FPGA is a field programmable gate array. Can you explain real quick what that is?
Yeah, sure. So field programmable gate arrays, the whole concept started a little over 30 years, maybe 35 years ago. And the idea was to provide digital logic integration in a form that was programmable by the customer who purchases the product. So you can buy a device that has no function until you program the function into it. And this started off in the late 1980s with devices that were collections of several hundred two-input NAND gate equivalents. And very quickly, these devices increased in density and increased in performance so that by the time the mid-90s arrived, they were capable of integrating many tens of thousands or even 100,000 two-input NAND gate equivalents. And the beauty of the technology was that it didn't matter if you were producing end product in the quantities of a few units, a few tens of units, a few hundreds of units, or even a few thousands of units. These were a cost-effective way of integrating digital logic technology into your end product. Historically, the only way to integrate digital logic was to build a gate array or a standard cell ASIC, which would require a large upfront non-recurring engineering charge and would also require a fairly lengthy fabrication cycle time. But with an FPGA, you could buy onesie, twosie kinds of quantities for relatively low amounts of money,
Mhm.
and you could program them at your desktop very, very quickly. So it was really an enabler for smaller companies to get into the market with products which required digital logic integration. And to tie all that back into space, the space market historically has been very much onesie, twosie kinds of quantities, because historically satellites would be built one at a time. And so you didn't need tens of thousands of components all performing the same function. You would typically need, 2, 4, maybe 10 components performing the same function. So FPGAs have always suited the space market very, very well. Even in today's proliferated LEO environment, where we do see satellites being built in quantities of dozens or even hundreds, maybe even thousands, it's still relatively small quantities relative to other areas of the electronics market. So FPGAs still work very, very well in space applications.
Interesting. So that means, and I think you both said something similar, that there has been a shift from geostationary satellites and now more smaller satellites are being deployed into what you call LEO, low Earth orbit. How did the hardware components or the requirements change, and what were the challenges?
For low Earth orbit, we're talking about 1,200 kilometers roughly above our heads, and these satellites orbit the Earth in LEO, and you can do some maths, but basically they are circling the Earth or the point above your head every 90 minutes. So from a thermal stress point of view, it's quite a stress because you're in the sun and out the sun. In the sun, so you're permanently being heated up and cooled down, which certainly creates some challenges for satellite designers to make sure that things are all able to survive such thermal stress. But the other big trend was that the customers started wishing to use lower cost components. So traditionally, geosynchronous satellite would use vastly expensive ceramic parts, and now the customers wanted to use lower cost plastic parts. So that was a big trend. But getting suppliers to supply little quantities of plastic parts with lots and lots of test results and radiation tests is not an easy thing. So again, the suppliers adapted themselves, brought out new product ranges, the things like rad tolerant, so radiation tolerant components, because at the end of the day, even though it's sort of flying above your head at 1,200 kilometers, you cannot forget about the impact of radiation on your satellite. So you have to design to make sure that the part is able to survive the various different radiation types that are up there. And that is one of the things that we have the most discussions with, I guess, with customers, is how does my part react under radiation? And you can have one part that's great, but if you forget the power supply or the clocking or some other part of your system, it doesn't work anymore because it's been hit by some radioactive particle, then your whole satellite potentially might not work. So the whole thing, it's a system consideration, but I think the message we're always discussing with the customers, you cannot ignore the radiation. Ken, I don't know what you got to say on that point.
Yeah, so I think you hit the nail on the head, actually, Paul. There's major challenges with flying components in space, and in low Earth orbit, as you said, you're orbiting once every 90 minutes, and depending on the inclination of the orbit, you can be going into the shadow of the Earth once every 90 minutes. So the satellite is subjected to these repeated heating and cooling cycles, which are really intense. So being able to survive the temperature cycling that comes about as a result of that is really a big challenge for satellite design. Radiation is a major concern for anyone who's flying anything in space. Low Earth orbit is about the most benign of the radiation environments that we encounter in space, but it's still pretty harsh compared to being down here at ground level. So in low Earth orbit, you're subjected primarily to a proton environment with a little bit of heavy ions, particularly as the inclination of the orbit increases. But we see that there is a proliferation of programs that are flying in low Earth orbit. And the reason for that is because if you're doing any kind of Earth imaging, you want to be as close to the Earth as possible. So you're going to fly in low Earth orbit. If you are doing some kind of communications, you want to minimize the latency, the round trip delay of the communication signal going from the Earth to the satellite and back to the Earth again. So, of course, you want to be in low Earth orbit for that reason. So that's why we see low Earth orbit increasing. But having said that, it's not that geosynchronous and other orbits are decreasing in the number of satellites that are being launched to those orbits. We still see a large amount of geosynchronous satellites. We see other orbits as well, such as medium Earth orbit, cislunar orbit, all becoming very interesting. Science missions flying out to the Lagrange points, which are actually halo orbits. So they're a compound orbit, essentially orbiting the sun, but also orbiting the Lagrange points, which are points. There's a series of them where the gravitational fields of the Earth and the sun and the moon are balanced. So in that environment, science satellites are subjected to very harsh radiation environments as well, with heavy ions comprising the majority of the charged particles that are affecting the parts. So radiation, you cannot attempt to fly in space without considering radiation. So one of the things as a supplier of components that are going into radiation systems in space, we do extensive radiation testing in protons and heavy ions and also in gamma radiation to simulate the long-term exposure of the components to radiation in space. We invest a lot in testing and reporting radiation. We collaborate with the space agencies such as the European Space Agency, other national space agencies in Europe, NASA and JPL over here in the US, of course. We do joint testing with them and with others to make sure that the radiation properties of our parts are well understood and that information is provided to design teams who are planning to use our parts in space.
We will take a short break. Stay with us. We will be hearing from our guests very shortly. This podcast is brought to you by Avnet Silica, the engineers of evolution. We help you bring secure, intelligent, and connected products to market. If you want to learn more about us, we have put information and links in this episode's show notes, and you can also connect with us on LinkedIn or avnet-silica.com. That's avnet-silica.com. And I think you mentioned something like alongside use cases, like you said, science missions, vector-based applications that are being used. So I'm thinking images of planet Earth. How do the components handle the processing requirements needed for those kind of use cases?
Yeah, it's an interesting question. So there seems to be an insatiable demand for processing capacity in space. And that's being driven by a number of different factors. There may be requirements on a satellite to do control of the satellite itself. So that's something we would call a satellite payload or a satellite bus application. So you have to do command and data handling. You have to do attitude and orbit control, otherwise called station keeping, to make sure the satellite is basically maintaining the right orbit and is pointed in the right direction. You have to do command and control of telemetry and making sure the satellite is obeying the commands from the ground station. So that requires some computational horsepower. But the biggest growth in computational horsepower is actually in the payload of the satellite. Okay. So I like to use an imaging satellite example here, but it applies to other forms of satellite payload as well. So if you think about imaging on a satellite, you may be imaging the surface of the Earth, looking for, for example, land use, looking at, whether land is being used for farming. You may also be trying to determine what kind of crops are being grown in a certain area of farmland. So you have an imaging system, so you can think of it as a video camera with a very, very long telephoto lens, and you're looking at the imaging data coming back in different spectral bands. So instead of looking at just panchromatic light, like you would be, as a human looking at an image in a camera, you might be looking at different frequency bands of light, including ultraviolet and infrared, and using that information to determine what sort of crops are there, whether there's crops at all, or whether the fields are being left fallow, maybe the status of irrigation or things like that. So you're looking at a vast amount of imaging data being captured and being brought onto the satellite. And, historically, when the image resolution was not that great, you may have been able to send that imaging data down to the ground for processing. Well, as you sample in higher resolution and with more spectral bands and with faster frame rate, the ability of the satellite to gather data exceeds the ability of the satellite to transmit that data down to the ground, because the downlink bandwidth is not expanding as quickly as the image resolution. So you have to do more processing on board the satellite. So initially, as this processing bottleneck started to arise, people tried to do compression and storage of data on the satellite and then transmit down to the ground as the satellite passes over the ground station. But we've exceeded that capability now. And so what we're doing is we're starting to make autonomous decisions on orbit based on the data that's coming in at the front end of the satellite. So now we're looking at different classes of processing that need to be performed. So we need to do some upfront image processing, perhaps using convolutional neural networks to look for particular patterns or signatures in the image data. And to perform convolutional neural networks effectively, now we have the need for vector processing capabilities in the hardware that's being flown in space. So we have a vector processing computational need. And then once the vector processing has been done, then you may have some application class processing that needs to be done to interpret what's coming out of the vector processors and to decide, okay, is this information useful? Do we send it down to the ground, or do we send it to some other space asset? Do we transmit decisions rather than transmit data to other space assets or down to the ground? So, now we have application class processing working hand in hand with vector processing, and we may, in the same system, also have DSP types of signal processing stuff going on as well to perform some of the RF modulation to transmit data or decisions out of the satellite and to other assets or to the ground. So this huge proliferation of computational resources needed on board the satellite.
So, Ruth, I was just going to say the whole of the image, sensing, the ability to take high-resolution photographs from a satellite has opened up so many interesting use cases, like forest fires. I mean, everyone's seen the horrific fires around the world. So there are now many companies looking at all types of forest everywhere in the world to see if there's, fires starting out. We have also the ability to look at particular areas of interest where deforestation is taking place and look and compare photographs over a short time period to see if all the trees are still there. Simple things like that. That tree's disappeared in the last 90 minutes. And obviously the whole climate satellite capabilities of what they're able to do now is quite phenomenal. And Ken mentioned this ability to process data on board. And this has opened up another new area, which is inter-satellite communication, laser terminals that are able to send high speed data, 8,000 kilometers, up to 8,000 kilometers to the next satellite. So maybe you're over the Pacific Ocean. Maybe you're nowhere near a base station to download all this lovely data you've got on your satellite. So what you do, send it round the globe via laser terminal up till it's above the base station and then send it all down there. These are ideas that were like 5 to 10 years ago, just not possible. Throw in all the artificial intelligence, the machine learning, the ability to say that picture's good, that one's bad. Oops, here's something about to hit my satellite. I think I'll just move out of the way of this piece of debris that's flying around the low Earth orbit. It's something else you have to sort of consider as you're designing your satellite. Hey, what's up there as well? What am I looking at down below and what potentially could hit me? The statistics of all the different bits and of rubbish that is up there that are being tracked. These are all things, you have to just add into the mix when you're designing the satellite. But, Ken's given a very good overview of the capabilities.
It's really incredible. And there are days where I can't even wrap my head around radio. And then here we are talking about what else is floating around in low Earth orbit, right? I imagine that with all these challenges and this new exciting space frontier and the fast evolving landscape, collaboration is of the essence.
Yeah, I mean, from our side, so Ken is AMD, a very important part of our portfolio of what we go to talk to customers about. But we have some other interesting guys, particularly doing the power supply, some small microcontrollers to do housekeeping functions. And to me, it's very, very important that the suppliers are talking to each other from a point of view of making sure that we have a power supply, for instance, that can support the quite complex needs of Ken's FPGA, as it's not a trivial matter, yeah? But if someone's already done that design, communicated with AMD, make sure it's all worked, hey, then that's half the battle, and it's a good help for the customers. From the point of support to our customers, we have a very, very close relationship with all of the customers, I would say, that we're dealing with. It really is a partnership from the supplier side, from our side to the customer side. It really helps immensely to have a very, very close relationship with your distributor and your supplier. Ken, I don't know if you probably confirm that as well.
Yeah, exactly. I think it's critically important that we have these strong relationships with other component suppliers in the market, because at the end of the day, while the FPGA or the adaptive SoC, which AMD provides, well, that might be providing the vast majority of data path signal processing in the satellite. Without the appropriate power supply components, without the appropriate clocking and timing components, and without the appropriate external memory components, the adaptive SoC or the FPGA, cannot do its job. So it's critically important that we have relationships with other suppliers and with distributors such as Avnet Silica.
Is there a use case or a recent project you could share or are free to talk about, the both of you?
Yes, one thing we can point to is the collaboration between AMD and Renesas in their power supply. So Renesas has a power supply or set of power supply components which supports the Versal, AMD Versal adaptive SoC. And there is a press release that was announced by Renesas in July, providing more information on that.
Sure. If we look into the future, what do you think will be the next major innovation or even challenge in space tech in the coming years?
We started off talking about all this new space stuff, and some of the customers were saying, okay, we want 1 to 2 year, 3 year lifetime up there for products flying in that orbit. And now it's been pushed out to 5 to 8 years. And now we're having customers that would say, well, actually, we would like 15 years, similar to ceramic parts, more expensive, but using plastic. And we have suppliers that are now producing radiation hardened, not just radiation tolerant plastic parts. And I see the trend going towards 15-year lifetime mission time support for plastic type components with additional screening and lots and lots of radiation testing and life testing and all those sort of things, because I think that's where the customers are going to want to be. Maybe price not so important, but life, the ability to survive for 15 years in low Earth orbit environment, I think would be quite a strong trend, plus all the just general trends from everything that the likes of AMD are able to do. And what we've seen today is phenomenal. I'm sure there's even more exciting things coming up.
Yeah, I think what I'm seeing is there's a desire on the part of companies who are building spaceflight hardware to come up with something that's being called in the industry the software-defined satellite. What's meant by that is that manufacturers of satellite subsystems want to be able to control under software what function their platform performs. So, for example, you may have a supplier who wants to sell a particular piece of equipment into a low Earth orbit satellite program and a totally different geosynchronous satellite program. So environmentally, the platform that they create has to cope with the worst of all possible orbital scenarios. So they have to cope with the thermal challenges of low Earth orbit, where you're temperature cycling once every 90 minutes. They have to cope with the high radiation environment of geosynchronous. And that poses some significant challenges, while at the same time they're performing a high throughput computational function in that system. And what we've seen over the last few years is that the traditional components that are being used for space application or for space computing applications are not able to satisfy the demand for high-speed interconnect using ceramic packages.
Okay.
So once you exceed about 12.5 gigabits per second per lane, ceramic package technology starts to run out of steam. And we've seen design teams looking forward. They're not deploying serial transmission standards at 12.5 gigabits or higher today, but they're certainly looking to that in the near future. In fact, we've had conversations with people who are attempting to exceed 25 gigabits per second per lane in future space systems. And ceramic packages just simply cannot keep pace with that amount of data interconnect between components. So the whole industry is being forced to go to organic packaging technology in order to satisfy this demand for high-speed interconnect. And we're in this environment today where, designing for the future, we have to be able to support software programmable computational resources in low Earth orbit and in geosynchronous and everywhere in between using organic packages. So that's the challenge that we have in front of us. The thing that AMD is working on currently is coming up with components which are integrated into organic packages, which meet the needs for long duration space programs, which are going to fly in the harshest natural radiation environments in space.
So I guess if you both say the time now is exciting, I guess we can look forward to another exciting 10 years in the future as well, right?
Definitely. We're looking forward to it.
For sure, yes. I think things are only going to get more exciting as we go on here.
So, Ken and Paul, it has been super interesting and fascinating to listen to your expertise and get some insight into new space. Thank you so much for being on the show. This was Avnet Silica's We Talk IoT. If you enjoyed this episode, please subscribe and leave a rating. Talk to you soon.